Yeah, welcome to this part where we are still working on set properties. And this part we are covering the identity property of a set. And in identity property of a set, we say that empty set act as an identity in an union operation. In an union operation, we take empty set as an identity, whereby we are saying that now A union empty set, which is an A union uh, null set, we get this A, and that is just clear that when let A, B, C, you'll find that when you take the A, B, C, and you do that union operation with an empty set, you'll still get that A, B, C, D. That is why we are proving that way. Then another one is that when you say that A intersection union, this means that universal set act as an identity in an intersection operation. So in our intersection operation, we are using identity as a universal. So let's see a universal set of sometimes we call this way, or it can be have a symbol of U, so that it's having A, B, C, D, E. Then you'll find that A, we are taking that it's A, B, C. Universal set, these are all sets under discussion, all elements of a set under discussion forms a universal set. We covered it in our introductory part. So here you'll find that now when you take A intersection union, and that is A, B, C, that is a set A, and then union our then intersection our union, that is A, B, C, A, B, C, D, E. You'll find that now we are looking at which elements are present here and here, and you'll find that A, B, C is present on both the two elements, and the three A, B, C elements are both present in set A, and then A, B, C are then present in the union, which is all items under discussion, and that we'll find that we'll get that is A, B, C. That is that after that intersection property. So you'll find that now A intersection union, you get A. It is true. This is A. These are the elements of A, B, C, and you're getting A, B, C after the operation. So this shows that we are now proving what we call an identity property of a set. Then again, we have another part which we are going to, which is part 5. We call it idempotent property of a set. And in idempotent property of a set, we are talking about union and intersection when applied to itself, it reverts, meaning that union and intersection reverts when applied with itself, meaning that any operation that is two operation, that is union operation and intersection operation, when you do it repetitively to the same set, the result is the same set. So let's see here that operation. Let A be 1, 2, 3. Then now, if you take A union, you take A now, if you take A union A, you'll find that A union A, elements common in A and then elements common in A, it means that those are elements in A. So you'll find here that 1, 2, 3, they are in A. 1, 2, 3, they are in A. So you'll find that union, you have to write, take all the elements both in A and B without repetition. We don't write repetitive. Let's say you take 1, it's both in the both A and A, 2 both A and A, then 3 both A and A. And then it means that now you're getting that A union A equals to A. We have proved this one. Then now let's look for the second one, which we are talking of intersection. We'll find that A intersection A, you will get A. And then you'll know that A is 1, 2, 3. Then intersect with another which is 1, 2, 3. You'll find that which elements are common. All the elements are common. You just find that there are 1, 2, 3, and this one now it is the A. the A we are talking of. That's why now it's proved that A intersection A, truly it's A. Again, in our first part we are talking of again, and this is an intersection. When you revert intersection, this is what you get. Then you take A union A, you still find A, and this is what you call union operation. When you apply it with itself, that is, you are doing an operation with the same set. The same way when you're doing an operation with the same set, using the union operation, you get the same set. Then again, when you're doing the same operation, using intersection operation, you get the same set. And that is called idempotent property of a set. And let's do let's tackle the last one, which is now we call it the complement, we just call complement property of a set. So in complement property of a set, we have the first one is we're talking of complement laws, whereby we are saying that the union of a set and its complement gives a universal set. What you have to understand is that when you have a set A and then you have a complement of A, this means that all elements in A are not all elements in A, you have to remove them so that you get what you call a complement A. That's why you say A union A complement, you get the universal set. Let's do a simple example here. Let universal set be A, B, C, D, E. This is now the universal set. Then let A, B, C, D, E. That is A. Now, how can we get the A complement? These are the elements that are not in A and they are universal set. So you'll find that it's A, B. A complement is A, B. Now, when now you take now the same A now, union A complement, you'll just get universal set, and that's A, it is C, D, E, and A complement is A, B, and then you'll find that all the elements here after that union operation, find that you're getting that A, B, C, D, E, and this one is what we call the universal set, and we have proved that first property. Then the other one is talking of intersection. You say that when you take A, then you intersect with A complement, you just find a null set. Truly, because the elements in A are not those elements found in A complement, so automatically we'll get that is a empty set. Now let's prove A. We have in A we have it is C, D, E. Then these are the members of A. Then A complements you are getting that is A, B. So which are common elements here? We don't have any common elements between the two sets. So you find that there are common elements here. That is just a null set. That's a null set. And then you find that you have proved that surely A intersection A complement, you get A. And then a complement can be written as the other books are saying a complement, that's one of them. Then you can be writing A that the same complement, then you can write A complement. All these are the signs of a complement. And I think we have come to the end of the set property. No, we will still have some part. We have again to clarify on this part where we're talking of law of double complement, whereby if you have an A complement again, then you complement again, you'll find that is A. This means that when you have A complement, now let's just let A be 1, 2, 3. Just do that simple, then confirm it now, and then let the universal set be 1, 2, 3, 4, 5. Yeah, simple that. Now A complement. How is A complement here? Remember that are not in A. There are 4, 5. Simple. Then again, complement again. complement of this one. Now members that are not in A complement, they will be now 1, 2, 3. Now the elements now which are the complement of complement, find that members which are not here and the universal set, there will be 1, 2, 3, and this shows that you are getting that now these are the A, and these are proof that now A complement again into complement you get A. It's truly A complement, then you complement it, you get A. That's why you are getting there. That we call it the law of double complements. The law of double complements. Then the other one is the law of empty sets and universal sets, whereby you say that universal set complement you get a union, and again we say that union complement you get a universal set complement you get an empty set complement you get a universal set. So you can just prove it very simply that our universal set here is let the universal set be 1, 2, 3, 4, 5. Then when we talk of universal complement, it means that elements that are not in a universal, and that automatically is an empty set, because we don't have those elements, and that's an empty set. We don't have those elements, and that's an empty set. Then again we are talking of empty. Now complement of an empty set, and know that empty set there's no set. Now the complement of an empty set will be automatically the universal set. Now the universal set here will be, that will be now 1, 2, 3, 4, 5. That will now be our universal set, and that shows that empty null complement equals to universal, and then universal complement equals to null set, and that is how we prove that one. And then thank you for listening, and we have reached to the end of this part. Now I think we have now finished what we call the properties of a set, and we have known that sets have 6 properties as per our research, and what we have presented is that the properties are, these are properties of a set, and these we have found that our first one we have what we call commutative property, then the second one we have what we call associative property, then the third one we have what we call distributive property, and then the fourth one we have what we call identity property, and then the fifth one we have what we call idempotent property, and then the last one, which is sixth one, we have what we call complement property. So thank you for being our viewer. Please subscribe to Carl Academy, like, comment, and share. This will give us that room to rectify areas that we have not covered fully. Goodbye.